So, we said that a embedded system, let's go with designer, what this person is trying to do is put together the electronics of the product, and the way you do that is through chip selection, which is deciding which SoCs you are going to put together. Those SoCs or system on chips modules, system on chip or system on chip modules can come from many different sources. You might buy a Bluetooth chip from Real Tech, for example, or you might buy a Bluetooth module from somebody who's already bought the chip from Realtek and put the module together. Similarly, you might buy something from Qualcomm, you might buy something from Texas Instruments, so on and so forth, with the intent that okay, now I am going to, as the embedded system designer, I am going to integrate all of these different chips into the product, right. So, there is chip selection and there is also chip integration, and chip integration is both hardware and firmware. So, these are at very high level the two responsibilities that that an embedded system designer has, and there are, like I said, many different knobs that the embedded system designer is trying to optimize. One of the conversations we had over the last few modules is the point about exactness, that it is engineering design by definition is an optimization problem, and an optimization problem means that you have 5 different parameters that play into the decision, and you are constantly weighing the pros and cons of each of your decisions in the context of these parameters, right. So, what are those parameters? The parameters of interest are, first, performance, which is whether your product will deliver what you promise it will deliver to customers. Then of course is price. All of us, for example, have a certain expectation of a 2000 rupee product. If we are paying 10,000 rupees for a product, we have a totally different expectation. Even if the, let's say we talked about a Bluetooth headset, you can get a Bluetooth headset maybe for 1000 rupees today, you can get something for 50,000 rupees. I think the AirPods Max is 50,000 plus. Obviously, you are not going to have the same expectations of these two devices. So, there is a customer expectation that is driven by the price that they have paid. So, that is a parameter that the embedded system designer needs to comprehend. Then there is reliability, which is that again, I think the example I gave in the previous module that obviously continues to be valid is you can, when you buy a product, you expect a certain lifetime out of it. You assume that okay, this is an investment I am making for maybe the next 3 years, 4 years, and you don't expect that product to go kaput in a week's time, right. And it is the embedded system designer's responsibility to say, yeah, we have enough confidence in the aging characteristics of this product. We have enough confidence that whatever the customer tries to do, it is still going to be robust. It's been designed in a robust enough manner that is not really going to impact operation or performance. That's a guarantee that the embedded system designer has to deliver to the customer. So, performance, price, reliability. For the most part, what we deal with are portable devices. Portable devices come with batteries. Batteries have to be charged, and how often one needs to charge the battery is a point of irritation, right? So, a customer might say, if you're for example, when the first headphone devices came out, you had to charge, I think the lifetime you got was like 4 hours, 5 hours. And you imagine, and I think there was, again maybe digressing a little bit, but there are these interesting nuggets of how people think about these things, not in the context of battery. So, when, or maybe in the context of battery. So, when the iPod was introduced, right, there were 2 things that the iPod guaranteed. One was that your entire music library can go into that device. So, as a user you say, oh okay, it's very easy for me to understand what that means. The second guarantee it gave is with respect to how long you can go without charging your battery. At that point, at that time, this was 98, 99, airplanes didn't have a USB socket for you to charge your portable device, right? And Apple made this claim that you can go on the longest transatlantic flight and still have charge left. So they measure time in terms of an activity that the user does, and the point being that as users we tend to say, okay, don't. Let's say I'm using the product, I'm listening to music, I'm doing something. At that point, the last thing I want to do is go look for a charging point, right? It completely breaks my flow, and as a customer, I don't want it. So power dissipation or power consumption is a very important care about for the embedded system designer. These are all easy to measure, easy to comprehend. There are two other parameters that are important. One is the type of package. So let's say I'm selecting different SoCs. All these chips come in many different packages depending on the number of pins, number of balls, so on and so forth. And as the complexity of these packages increase, the complexity or the reliability of how well can I solder, what is the cost of assembly start to get into play. So at some level it has a tie into price, because a more complex chip needs a more complex PCB, also needs a more complex assembly process, thereby increasing the price. So type of package is a very important consideration in that context. The last care about is the form factor of both the PCB as well as any chips that go onto the PCB, right? I mean, you want your product to be a certain size, that is the customer aspiration. That product size translates into the size of the battery, size of the PCB, and the size of the PCB translates into the size of the chips you can use. Form factor is just a nice word for size. So it is automatically follows that it is important for the embedded system designer to constantly keep reminding themselves that, oh, there are these 6 parameters that I have to keep focusing on, which is performance, price, reliability, power consumption, type of package and form factor. And any subsystem I design, I need to think about that design of that subsystem in the context of these 6 parameters. That is how you would expect an embedded system designer to think and work on their set of challenges. Let us continue. What we are now going to do is look at these 6 parameters in the context of the charging subsystem. So let me just so we are going to keep this here, so we constantly remind ourselves that these 6 parameters are important. And what we are now going to do is look at so we are going to look at a charging subsystem in the context of these 6 parameters. So it's many times we are used to sitting in classes where you are constantly thinking what is the answer to this problem, right? A very natural trait that maybe in some level our education system encourages, where somebody will ask you questions and you give out answers and you are graded on the quality of your answers. But lot of design is really not about answering questions, it is about asking the right questions, right? And what design philosophy encourages is the asking of questions, right? It is important to put yourselves in the shoes of the customer and say, okay, if I am the customer, what all will I want, right? What attributes are important to me, right? And suppose you say, oh, okay, this is a device, it's a portable device, you can charge it, it's a chargeable device. As a customer, what all will I want to do? Asking those type of questions is what really drives the quality of design, because once you ask the right questions, the answers will automatically follow. So, in that spirit, what we will now try and do is try and ask ourselves some of these questions in with respect to the charging subsystem. So, let's act like customers and say, okay, what all will I want from a charging subsystem? So, the first question I will ask is, how fast can I charge my device? Right. This is now whichever product you are building, you would see that earlier it used to be for how fast you can charge your laptop, how fast you can charge your phone. Now, how fast you can charge your electric car is a matter of is a performance metric, right? And it is important for the user because charging is an interruption with respect to using the product. So, the user will want to know for how long are you going to keep interrupting and how often are you going to keep interrupting. So, how fast can I charge my device is the first question. What would be the next question? So, I mean, you think about this, right? If we are in Chennai, in Adayar, I don't know if it is true in Chennai, it's definitely true in Bangalore, where on let's say you're driving somewhere, you stop at a traffic signal, there is a very reasonable probability that somebody at that traffic signal is selling a charger. So, you can now go to an Apple store and buy a charger, or you can buy a charger at a signal from some a guy who's just peddling, I don't know, second hand, third hand, who designed it, how the components were sourced, that class of solution. And what you want to do is say that you're buying my product. Let's say my product is 10,000 rupees. Now, when you're buying my 10,000 rupee product, I can't tell you don't use that charger, because you're as a customer you're free to use whatever charger you want. But what I have to guarantee is that 50 rupee charger won't come and spoil my 10,000 rupee product, because at that point all of that customer's anger is going to be directed at the person who made that 10,000 rupee product, not the guy who sold the 50 rupee charger. So, it is important to be able to say that it can work with any charger. So, the question that the user will ask is, can it work with any adapter, right? And when you ask this question of can it work with any adapter, right, what exactly happens from an electrical perspective? Now, the challenge with buying things from places like traffic signals is that you assume that okay, there is no regulation on the design, regulation not by way of law, but by way of electronic design, right? That let's say you have to take a wall power supply, you have to step it down, you have to sort of what is the word for that? I'm missing the word. So, let's say you have to convert from step it down, convert from AC to DC. You want to be able to say that okay, after all of that conversion, there will obviously be some transient characteristics. You can guarantee to the user that okay, my DC voltage, suppose I am rating it at 5 volt, is going to be 5 volt plus minus something. That's the DC voltage, and that maybe is a reasonable confidence. But when you turn on that power supply, when that 220 volt is applied to one end of the coil, what are the transient characteristics that will be seen at this 5 volt output? That is very hard to guarantee unless it is designed well. So, it is possible that it will come to 5 volt, but for a brief period of time it might go to 15 volt, it might go to 20 volt. Now, what the customer will want from any product he buys is, let us say there is some nonsense happening in the charger, just protect me from it. Right? I do not expect you to charge the device when that happens, but at least make sure nothing happens to the device. So, can it work with any adapter? We can extend that to say, will the charging subsystem protect the device from high voltage transients, right. So, that is the second question that the user might ask. What else might they ask? You think about electric vehicles, right? And you see every once in a while there is this news that there was an electric vehicle that went up in flames. So, somewhere in the end user's mind there is always that concern that battery means possibility of fire. Battery, somewhere that battery charging activity is not safe. There is in the layman's head that fear is there. So, okay, if suppose I translate that into an electrical statement. What if the battery is faulty? What if the battery is shorted? How does the charging subsystem deal with it? Because it shouldn't say, okay, that battery is shorted and it keeps trying to charge it is just waste of energy and there is the risk that something can happen. So, it is important for the charging subsystem to protect against faulty batteries. So, what will the charging subsystem do if the battery is shorted, right? This is something that as a user they will be concerned about. As a related statement, right? Now, batteries, again we associate fire, heat and all that together. So, what happens if the battery heats up? What should the device do? Can the charging subsystem protect me when and you might have noticed this, right? When you plug in your phone to charge, you try to touch your phone, you will see that it is getting hot. The activity of charging involves a fair bit of heat dissipation that will worry any user. So, now if the temperature is starting to get very high, if the battery is heating up too much, is there something that the charging subsystem can do? Right? The user might not lead on to this, but the user will think, okay, anything that is potentially unsafe will my charging subsystem protect against. So, you say, okay, now let us say in peak summer where the ambient is already 50, 55, if you are trying to do charging somewhere outdoor, right? Or you place the charger on let us say you have a battery bank. You are sitting and chatting with your friend on your motorcycle and you say, okay, I am going to leave this with the power bank connected to the device so it can charge. I am just going to leave it on the petrol tank for a minute, right? That is again ambient temperature is very high. So, it is very possible that it might very quickly reach a temperature where things can start to get unsafe. Now, the way battery chemistry works, it can be unsafe both in very hot zones and very cold zones. Either is a case where, because again if you've ever seen a data sheet for a product, and we're going to look at one in a bit, you would notice that they would mention an operating range. Batteries also have operating ranges, and battery operating range is typically -5 degrees to 60 degrees or so. And what it will do is, if the temperature is less than -5, it will not allow charging. Now, this is something that the charging subsystem has to take care of. So, the charging subsystem has to say, okay, there is a standard that drives when it is safe to charge a battery and when it is unsafe what I am allowed to do. Now, is my charging subsystem adhering to that standard or not? So, what happens if the battery heats up while charging, and what happens if the ambient, I won't say ambient, we will still stick to battery, if the battery temperature is too low, right. So, at some level these are the 5 questions that a user might think about when they think about charging. They might really not care about what package you use, what is the form factor, that's irrelevant to the user, right. They might also wonder what charging port you provide, so which is a PCB decision. So, we will put it just for completeness sake, what type of charging port is available. Which is, we talked about the point that the embedded system designer's responsibility is chip selection, integrating those chips into hardware and software. Part of that is also saying is decisions on type of connectors. So, for example, you might say, okay, I am going to use a USB-C connector because USB-C is the most prevalent standard today for charging. Most charging cables come with USB-C. So, that is what I am going to do. That type of decision is there for the embedded engineer to make. So, we will list it here. The other 5, how fast can I charge my device? Can it work with any adapter? What will the charging subsystem do if the battery is shorted? What happens if the battery heats up while charging? What happens if the battery temperature is too low? All of this come down to design of the battery charging subsystem and selection of which charger IC we use, right. That is what we are going to look at next. So, now when we talked about charging subsystems, and I think through the course of these modules we haven't drawn even one amplifier yet. So, we will get, I promise you we will get there, and we are going to get there very soon. But before we get there, let's continue to operate in the same model, because I think if we can ask ourselves questions and work in block diagrams, then our understanding becomes so clear that it is possible for us to then say, oh, okay, now that I have the understanding, I know exactly how to architect the system. So, in one of the earlier modules when we talked about the, so let's say charging subsystem, I'll say super, we won't even say high level operation, I will say super high level operation is that somewhere it has 3 phases, right. It has a what is called a pre-charge or preconditioning charge, then it has constant current charging, what is also called as fast charge, and then there is constant this is this is constant voltage charging, there is no other name for it. So, the charging activity typically goes through these 3 steps. So, what happens is you plug let us say your device, plug the adapter cable into the device and then connect it to a wall power supply. What it will do is it will first go through a step called pre-charge or conditioning charge, where it is ascertaining the state of the battery and saying sort of wake up the battery to be ready for charging. That happens depending on the battery voltage, might happen for very little time. If you haven't used your device for 6 months, 9 months and it's completely drained out of charge, it might take some time before it comes out of pre-charge or preconditioning charge. And you might have seen this, right? Suppose you let your phone go all the way to 0. Right, you completely drain the battery, then as soon as you plug it in, it doesn't immediately start charging, or even if it starts charging, it doesn't immediately start displaying the phone percentage to you, because it is going through a state of ascertaining that, okay, my battery went into sleep, let me nudge it awake first before I actually start to give it lots and lots of current. So, that phase is called a pre-charge or a conditioning phase, so pre-charge or conditioning charge. Once you go past that state, you say, okay, now the battery is ready to take large amounts of current. So, I am going to transition into the fast charge mode where I am pushing high levels of current. And after the fast charge, you might, is very important again from a safety perspective that you do not exceed the rated voltage of the battery. So, because if you exceed the rated voltage of the battery, again you run the risk of bad things happening with the battery, which again delivers extremely poor customer experience, not to mention safety hazards. So what you want to do is, until you get close to the battery voltage, you want to dump large amounts of current to charge the battery, and once you get close enough, you want to say, okay, now I am going to start slowly reducing the current so that the battery voltage will asymptotically approach the rated voltage. Right, that is what we want from the operation. Right. So let's, again, this is what we want.